Welcome back to another explainer. Today, we're popping the hood to see what actually happens when an AI model gets smarter. And don't worry, we're not going to get bogged down in a bunch of abstract equations here. Instead, we're going to translate the world of calculus into a really physical, intuitive journey. Think of it kind of like a calculated descent down an incredibly steep, foggy mountain.
Here's our roadmap for that descent. 1. How AI actually learns. 2. The math of improvement. 3. Navigating the optimization landscape. 4. The engine, backpropagation. And 5. Tuning the learning speed. Let's dive right in.
Section 1. How AI actually learns.
Now, it's really fascinating to look at the contrast between the types of math at play here. You hear a lot about linear algebra in AI, right? But honestly, linear algebra is really just the conveyor belt. It just moves the data forward. Calculus, on the other hand, well, that's the compass. It points the way to a better model by telling it exactly how to improve. Without calculus, there's literally no learning happening.
But to actually learn, the model first has to realize it messed up, which it does by quantifying its mistakes using a loss function. Say we're predicting housing prices, we might use something called mean squared error. Or if we're sorting images of cats and dogs, we use cross-entropy. The key takeaway here is that AI learns by mathematically minimizing this exact loss.
Moving on to Section 2, the math of improvement.
So here's that compass we were just talking about, the derivative. In the context of AI, it represents something highly practical. It's the sensitivity of the output to a specific weight. The model is constantly asking itself, okay, if I tweak this one parameter just a tiny, microscopic bit, how much does my overall error change? This constant checking is what allows for stable, smooth updates.
And the size of that derivative dictates our next move. If we've got a massive prediction error, like standing on a really steep cliff on our mountain, we need to take a massive step downward to correct it. But if the gradient is shallow and small, we know we're getting close to the bottom, so we just carefully fine-tune our position. Baby steps. But here's the catch. Modern models don't just have one weight. They have millions, sometimes billions of them. So we group all those individual sensitivities, the partial derivatives, into one giant vector called a gradient. This gradient brilliantly points in the exact direction where the error increases the most. So, to minimize our error, we literally just turn around and go the exact opposite way.
All right, Section 3. Navigating the optimization landscape.
Imagine you're standing on this foggy 3D mountain terrain. Your coordinates, your x and z axes, represent all of the model's parameters. Your elevation? That's your loss value. Your ultimate goal is to find your way down to the absolute lowest valley possible. Training an AI is simply that continuous, calculated downhill movement.
But of course, this mountain is almost never shaped like a nice, perfectly smooth bowl. It has what we call a non-convex loss surface. Basically, it's treacherous terrain. You've got totally flat regions that bring learning to a crawl. You've got fake valleys known as local minima, or tricky little edges called saddle points that can completely trap our model. This is exactly why initialization, meaning where we randomly drop the model onto the mountain at the very beginning, is so crucial to our success.
Now, to safely traverse this terrain, we need the right vehicle, which we call an optimizer. Think of standard stochastic gradient descent as a super reliable tractor. It's a fantastic, scalable baseline, but it's really sensitive to the gears you choose. The Adam optimizer, on the other hand, is like a sports car. It uses momentum to adapt its learning rate on the fly, making it incredibly fast, super stable, and honestly the default choice for most modern models.
Section 4. The engine, backpropagation.
So how do we actually calculate all this across dozens or hundreds of layers of neurons? Well, that brings us to the chain rule. This acts as the mathematical backbone, physically linking the derivatives across all those hidden layers. It allows the network to take an error at the very end of the process and trace it all the way back through the chain to figure out exactly which weight at the beginning caused the problem.
It's beautifully simple when you think about it. Backpropagation is basically just the chain rule on repeat. The error flows backward, layer by layer. Without this incredibly efficient method of updating weights, training deep neural networks would be pretty much impossible.
It all comes together in this rhythmic four-step heartbeat. First, the forward pass computes a prediction. Second, the loss function measures the exact error. Third, the backward pass uses our chain rule to compute the gradients. And finally, the optimizer updates the weights. Wash, rinse, repeat across millions and millions of data points.
And finally, Section 5. Tuning the learning speed.
We control our speed down the mountain, our RPMs, if you will, using a crucial dial called the learning rate, often represented by the Greek letter eta. When we move in the opposite direction of the gradient, eta dictates the exact size of the step we take. It is arguably the single most important setting you can tweak when training an AI.
Because, honestly, it creates a classic Goldilocks problem. If you set the learning rate way too high, the model bounces violently back and forth across the canyon, completely missing the lowest valley. We call that catastrophic divergence. But set it too low, and the model takes these tiny, microscopic baby steps, meaning it'll take agonizingly forever to learn anything. You absolutely have to find that sweet spot.
And as we're driving down, we've got to watch out for hazards. Gradients can sometimes shrink down to zero, which we call vanishing, or blow up into massive uncontrollable numbers, which is exploding. Both of these cause highly unstable training. We counter these issues with clever techniques like ReLU activations and data normalization. And just to make sure we're actually learning the concepts and not just memorizing the data, we constantly monitor our learning curves to spot overfitting.
So, to wrap up our descent, let's review the big takeaways here. While linear algebra provides the necessary structure to push data forward, it is calculus that serves as the true learning engine of modern AI. Through the precise sensitivity of derivatives, the directional guidance of gradients, and the chain rule magic of backpropagation, models are mathematically driven down that complex optimization landscape to find the absolute best answers.
Which brings us to the end of today's journey, but opens the door for our next one. I'll leave you with this final, provocative thought. If calculus gives the AI its perfectly precise direction, how on earth does the model handle the inherently messy, random, unpredictable nature of real-world probability? Think about that for a bit, and join us next time on The Explainer as we tackle the probability basics of artificial intelligence. Keep learning, and we'll see you then.